Thank you, Luke, and good morning, everyone. I have to start with an apology, but somehow my voice got a bit rough overnight. It was probably the last bottle of whiskey, which I shouldn't have. No, I'm just a bit sore, but I hope my voice is going to carry through the presentation. So, to stay with the image that Fiona has created, when she said she's putting down the bonnet, I'm going to open it up very much again and look at one of the processes in UKCA that plays a crucial role in determining the composition of the atmosphere and has lots of implications for the climate system and the Earth systems, as I hopefully will be able to demonstrate. So what I'm talking about is dry deposition. And before I start, I do want to acknowledge all the people that have contributed to that work, that part in UKCA, but most of these people also contribute to many other things in UKCA. So I just want to make sure that you understand that this is not the work of just one person. I mean, Earth system modeling is very much a team effort, and it's virtually impossible to do that on your own. Thanks to everyone who contributed. So what will you be hearing from me in this talk? First of all, I would of course like to define what dry deposition is and explain a little bit how it works in reality and how it works in models. Then I'm gonna try to argue why we need it and why it's important, and then of course you want to know how does it work in UKCA, how have we implemented it, how are we working with it. In the fourth section I want to show you a few applications just to give you a sense of why we need dry deposition and what we are using the capability for and what kind of science applications we are using that capability. And I'm gonna close with a section on summarizing recent developments, recent publications, and give you an outlook on what we are planning to do technically in terms of model development and scientifically in terms of scientific questions we want to attack. And that should then bring us right through the coffee break, if I understand correctly, Luke. Okay, let's start at the beginning. What is dry deposition? So dry deposition can quite accurately be defined as the removal of gases and aerosol species by a turbulent transfer process towards the surface and then by uptake of these species at the surface. And it's called dry deposition because there's it's in opposition to another process which we call, quite unsurprisingly, wet deposition, which is actually washout of species. So this is really a transport process and not something that some washout of species from the atmosphere. Now, dry deposition is a very important thing for many atmospheric species, but for us as modelers, we are mostly interested in because it's actually, and I will show that later on, it's very important for the ozone budget. And we are, when we talk about dry deposition, most of us atmospheric chemists think about ozone. As I said, it's a turbulent downmixing process and then an uptake at the surface. So it does depend, obviously, on the structure of the boundary layer. It does depend on turbulent and diffuse processes, and the underlying surface structure plays an important role. It depends on whether you're above bare ground or above vegetation or open waters like the oceans and stuff like that. That makes all a big difference in terms of how effective dry deposition will be in removing species. And I have defined dry deposition as a removal process, but strictly speaking, we should actually talk about the surface exchange process, because for most species, there will be a flux in both directions. There will be a removal of those species, but there will also be a re-emission, actually, of the deposited species, or there will be another source in the vegetation or anything. So probably from the point of view of realistically representing dry deposition processes, thinking of an exchange, atmosphere surface exchange process is probably the better picture. But I will stick with the more traditional formulation of dry deposition for the rest of this talk. So to answer the question quite quickly and hopefully decisively, I want to look at the ozone budget, the tropospheric ozone budget, and on this slide, don't bother too much with all the complicated processes going on. What is important here are these main terms. This is what I'm interested in. So when you look at the chemistry of ozone in the troposphere, chemical production produces around 4,500 teragrams of ozone every year. This is balanced by almost the same amount of chemical loss. It's not, I don't really agree with that being the exact same term. It's not that chemical production and loss actually cancel each other out completely, because otherwise we wouldn't have any ozone in the atmosphere. But in this paper, they decided to say that these two terms are balanced. Then there is some influx from the stratosphere. Stratospheric ozone is mixed down through the tropopause into the troposphere, and then there's the deposition, removal of ozone at the surface, and this amounts to about 1,000 teragrams. So a quarter of the gross chemical production of ozone is actually removed at the surface through dry deposition, and that's why dry deposition is such an important process in the budget of ozone, and likewise for a number of other species. So how do we deal with dry deposition in models then? There's what we call the standard model, because everyone has used that approach for ages now. And this is actually using the analogy of an electrical circuit. So you represent the deposition to the surface in terms of a resistance to its deposition. And there are a number of resistance terms. There's the aerodynamic resistance, there is the quasi-laminar resistance, and then there's the surface resistance. And then you can, just like you would formulate the problem for an electrical circuit, you can formulate the deposition velocity as the inverse sum over the individual resistances. And then each of these resistance, well, especially the surface resistance, is actually a sum of individual terms, but we're going to come back to that later. So the aerodynamic resistance, and also I will talk about that a little bit more in coming slides. That depends very much on turbulent mixing. The quasi-laminar resistance is dominated by a diffusion process through the very last atmospheric layer, which is only a few millimeters thick above the ground, but it represents a quite strong barrier to deposition. And then there is the surface term, which depends on the structure of the surface. As I said, bare ground, vegetation, and so on. But we'll talk about that in more detail in a second. So on this slide, I wanted to show you how deposition looks like in our modeling efforts. So these are a number of, this is a comparison of models that have participated in an international effort which is called HTAP, Hemispheric Transport of Air Pollution, where we are looking at the impact of air pollution transport across continents. In this project, we are also looking at like how these models perform. And here you can see a comparison of the models that have participated at different sites across the globe. And the main point here is, I think, to point out is that while most models seem to agree on the shape of the seasonal variation in dry deposition, there is still a large spread amongst models in determining the actual magnitude. I mean, at least most models are in the same order of magnitude, which is already quite promising. But models do, as I said, agree on the seasonality. They do agree on the variation between different sites, but there is still a lot of work to be done in terms of improving the consistency of the representation between models. Dry deposition is also measured in the real world, which is good, because otherwise we wouldn't have the ability to evaluate our models. The problem, however, is that these measurements are sparse and usually short-term. So this is campaign work usually, which means it's limited to a site here in Amazonia actually, and it's limited to a few days or maybe a week or two if you're lucky. And that's really not enough to make a, I'm almost inclined to say, meaningful comparison between models and measurements. Which basically you can see here on this slide. Now, there is one positive aspect, at least, and that is that models and measurements do agree reasonably well on the magnitude of the effect. So the models do actually represent the deposition flux in terms of its magnitude quite accurately, but smaller scale like diurnal variation and site-specific properties are still very difficult to include in the models, because basically, as I said, it depends very much on the surface structure. So you would actually have to represent the exact composition of the vegetation, the exact chemical composition of the soil, and all that in a global model to be able to represent a site measurement. And that, of course, is impossible, because that would introduce so much detail in a global model that we wouldn't be able to run it. But, you know, there's a reasonable agreement between measurements and modeling, in the sense that we can confidently, to some degree, use dry deposition models in our chemistry, climate, and Earth system models. This work by Catherine Hardecker, she used the HTAP model ensemble results to look further and deeper in the comparison between different models, and also into the process of dry deposition itself. Shows you the importance of the underlying surface structure. So what she did is she analyzed the total annual ozone flux and the annual average ozone flux with respect to a number of surface types. So these surface types include, in black, snow and ice. Then there's deciduous forest, coniferous forest, agricultural land, grassland, tropical forest, and so on and so forth. And the interesting bit is, let's start with the bottom plot first. So the most effective surface type or ecosystem in terms of removing ozone from the atmosphere are the tropical broadleaf forests. So the forests have these plants have a very strong exchange between the atmosphere and the leaf interior. So they take up CO2, they take up air, they take up water vapor, and by doing that, they also take up ozone and other pollutants. and very effectively remove these compounds over the location where they are. However, tropical rainforests don't make up that much of the Earth's surface anymore. So while they are dominating in the annual average flux, they are not dominating the total annual flux. And the interesting bit here is, which was actually quite new, we as modelers weren't that aware of the fact, we just didn't think of it, to be honest. While over water, the removal of ozone is not very efficient. It's actually, the reason for that is that ozone isn't very much water soluble. So it can't be taken up effectively and efficiently over water. The Earth's oceans make up 2/3 of the total surface. So they are very, very effective in the total flux, because just because of the sheer area they present to ozone. And so the deposition over the oceans has become of much interest in recent work, and it's something that we have to really get our heads around and try to do well. Right, so this is the end of the first part of my presentation, and I hope I was able to define what dry deposition is, why it's important, how we use it, how the standard model in our modeling efforts looks like. Now let's look a little bit more into why dry deposition is so important and why it's worthwhile to spend time developing this process model further. So I've already said that dry deposition is an efficient removal process for both gas phase species and particulate matter. It's vital for ozone. I mentioned that. But it's also important for virtually every atmospheric species that has a certain amount of solubility in water. The most soluble a species is, and that usually means, in terms of chemistry, the more oxidized the species is. So in terms of oxidation, you go from an aldehyde, so like formaldehyde, to an alcohol, like methanol or ethanol, and then you go to an acid, formic acid or acetic acid, which is vinegar. And the more oxygen you attach to a molecule, the more polar it gets. So it has actually a plus and a minus, a residual plus and minus pole in the molecule, and that means it becomes water soluble, because water itself is a polar solvent from a chemistry point of view. So everything that is highly oxidized will be effectively removed by dry deposition, and likewise for the organic species. It is also important for aerosols, and it's particularly important for small aerosols, because large aerosols, coarse aerosols, are more susceptible to sedimentation. That is, sedimentation is simply removal by the gravitational force. They fall down, and their fall is somewhat broken by friction, but basically large aerosols fall out of the atmosphere, but small fine and ultrafine aerosols need to be transported down by mixing. So that's the difference here. Sedimentation is just gravity. Dry deposition is actually down mixing by turbulence. So I mentioned already that plants are very effective in removing ozone from the atmosphere, but that works, as I said before, by leaves mainly actually taking up compounds from the atmosphere. They assimilate CO2, they take up, they exchange with the surrounding environment, which means they also take up quite a lot of ozone. But that ozone is a very reactive molecule, and it is damaging to plants. So what happens is, even it's good for us that plants remove ozone, they are damaged. The leaves are damaged at a cellular level, the photosynthesis is impaired, carbon assimilation is reduced, the plants don't grow as much. They can even be damaged to the point where leaves die off, they age faster, and this reduction in productivity results in a reduction in crop yields at the end of a growing season. And it is known for quite a while that ozone damages to crops, to agricultural plants, can cause severe economical damage of the order of tens of billions of dollars every year. So apart from the fact that, as Fiona showed in her talk, a reduced carbon assimilation has impacts for the climate in terms of radiative forcing. The reduction in the effectiveness of photosynthesis has also implications for agricultural productivity, for food security, and that's another reason why we are actually interested in representing this process as accurately as possible, because we need to estimate these kind of effects in the future as well, because we need to inform policymakers about what's going to be the capacity of food production in the future. How will the ecosystems work in the future with increased pollution and so on and so forth. So this slide is making an argument along those lines exactly. There are two things. The reason why I put it up is twofold, basically. First, it's to demonstrate that leaf biomass is probably the most susceptible when it comes to damages by ozone, which is understandable because it's the leaves that actually take up ozone from the atmosphere. And it's also expected that the leaf damages will be growing substantially in the future climate and atmospheric composition environment. So future atmospheric composition and air quality will be defined by the change in climate, but also by the change in the emission from anthropogenic sources, which also drive the climate. And so that's why Fiona spoke about co-benefits. So if you can find a strategy that mitigates climate change, in many cases that also makes air quality better and has implications for things like ecosystem functioning, food security, and so on. Right. So we know, hopefully we know now what dry deposition is and why it's important. Let's look at how we represent dry deposition in UKCA in the model that actually you're going to use during the practicals or have been using during the practicals already. This list here on the left-hand side is a list of the species in UKCA that are subject to dry deposition. So it means like a lot of the chemical species in UKCA, and also I haven't put them up here because I'm an atmospheric chemistry modeler and I rarely look at the aerosol side of UKCA, but I shouldn't forget about the aerosol side of UKCA because UKCA is an aerosol chemistry aerosol model. So many species in UKCA are actually subject to dry deposition. And we use, as almost every other model, we use the Wesley approach, which is the resistance in series approach that I've explained before. For the gas phase species, this process is a bit more interactive. So we are using information from the land surface model. we are using information about solubility and so on, and the deposition velocities are calculated interactively. They are temperature dependent, they are surface dependent, and so on and so forth. For the aerosols, a slightly different approach is applied. In this case, what is done is surface roughness, or the roughness length at the surface, is, which is roughness length is basically a measure of how much vegetation there is, how far does it, how smooth or rough essentially the surface is, and that has implications for the turbulence above that area. The aerosol side of things makes uses roughness length to infer a surface type. It doesn't use directly the surface type, which could be provided by joules, and then prescribes a velocity above that surface type. This is just, I think it's a historical legacy, and we haven't really worked on that side of things to unify it with the approach in the gas phase chemistry side. But this is, you know, there's work to be done in the future. Fiona has shown you how UKCA is a part of either a chemistry climate model or an Earth system model, and there are other parts to these models. Quite specifically, we have a surface model called JULES, the Joint United Kingdom Earth Simulator, I think it's called. Sorry? Land Simulator, I think. Okay, thank you. I'm not good with memorizing acronyms, even though I'm on the steering committee for JULES. I'm sorry about that. I just can't remember these things. So JULES basically manages all these surface types. So JULES knows about vegetation. JULES is a dynamic vegetation model. It grows forests, it grows grasslands. It also removes vegetation if it dies off due to drought and stuff like that. Recently, we've added fires that can remove vegetation, and so on and so forth. So JULES basically provides us with information about the type of surface we are dealing with, and within a grid box you can have up to 27 different tiles, and in the most traditional, or in the oldest representation of these subgrid tiles, we would have 5 plant functional types, very simple, either broadleaf trees or needleleaf trees, C3 and C4 grasses. So the difference here is a difference in how the photosynthesis works, basically. So there are just 2 different ways grasses deal with that. And there are shrubs, and then there are non-vegetation types like urban or bare soil, water and ice. And water is, in my understanding, this is not meant to be the oceans. The oceans are separate, but this is lakes and rivers and stuff like that. In recent versions, we have increased the number of PFTs. We now have 3 broadleaf types, we have 2 needleleaf types, and so on and so forth. And then I think the Earth system model uses this configuration with 27 tiles, of which 13 are PFTs, part of them are crops. And there's I think 10 tiles are referred to ice. But, I mean, long story, short message. We take the information about the subgrid surface properties for the deposition calculation from JULES. And then you calculate the surface deposition resistance, and then you integrate over these tiles, and that's basically how the deposition velocity for a single grid box, the surface resistance part of the deposition velocity is calculated. And then there's, as I said, aerodynamic and quasi-laminar resistance as well. The good thing is that if there are any changes in terms of the underlying surface tiles, you don't need to change the code to take advantage of that. That's just done automatically. So you can change the underlying surface structure by changing the configuration, meaning via ancillaries or switches in the rows editor, but you don't have to change the code and recompile. And on this slide, I'm summarizing in a small sketch the way the code works. So this is for the, I should say, this is for the gas phase side. This is not the way it works for the aerosols. So you have calling routines at the top. There's in principle, there are two ways of using dry deposition. One is the fully interactive, one is an older one which uses, in the end, something like prescribed deposition velocities. The option is there, I think, but no one uses it anymore, really. So maybe in the future we're going to take that out even. So you come in via the chemistry control routine that calls the deposition control, and then you have essentially one routine that takes care of aerodynamic resistance and quasi-laminar resistance. Then you have another routine that calculates the surface properties and the surface resistance, and then a third one that puts it all together and calculates the grid box integrated dry deposition velocity and flux. So it's on the whole, it's a rather simple model, and I like simple because it's easy to control and easy to understand. So usually that helps in avoiding big mistakes. We make them nevertheless, but anyway. So let's have a look a little bit into the individual terms. So this is how mathematically these terms are represented. The aerodynamic resistance depends heavily on the stability of the boundary layer, because I said this is mostly determined or determined by turbulent mixing processes. So surface roughness, surface structure plays a big role, but it's independent of the species. So there's no species dependent in it. Now the quasi-laminar sublayer resistance, as I said, that's diffusion. That's a diffusion process through the very last layer of the atmosphere. That is heavily dependent on the species, because diffusion is a process that's very much dependent on the structure of the molecular weight, and so on and so forth. So it doesn't depend on the boundary layer structure, and it doesn't depend on turbulence, but it does depend heavily on the species. These terms are really individual. This term is the same for every species. This term is different for every species. And then finally, there is the surface resistance, which is the last step to actually the surface uptake, and that depends on everything. That depends on turbulence, that depends on species, that depends on anything you can think of. So surface type, water, ice, bare soil, and so on and so forth. If you're over vegetation, there's stomatal uptake, there's something in relation to soil moisture. It depends on the time of day, because temperature plays a role. The vegetation itself simulates CO2 during the day and respires, exhales, you might say, during the night. So the direction of the flux is different in terms of time of day. Then there are non-stomatal uptakes. There are uptakes via the stem or the twigs or the bark of a tree or a plant. Whether it makes a big difference whether you have large leaves or small leaves. Like think of broadleaf trees, broadleaf trees in comparison to needle-leaf trees. We measure that in a quantity called leaf area, and the leaf area is basically the ratio of the total leaf area to the surface the tree projects on. So if you would like shine light on a tree from the top, it would make a shadow on the ground, and that's sort of the area that the tree occupies in terms of ground. But then when you integrate up over all the area of every single leaf on that tree, that's much larger than just this geometric area that it occupies. So this is measured by a leaf area in the models typically. And all these calculations that are necessary for all these individual resistance terms that make up the surface resistance is done in UKCA's, in this routine in UKCA. And this is the routine that also makes heavily use of information from joules. So this routine is where UKCA is strongly coupled to the surface model. One area where UKCA is heavily coupled to the surface model. All right, I hope I've given you somewhat of an idea how we are dealing with dry deposition in UKCA. I think you will not be able to play around too much with surface dry deposition in your practicals, because if you want to make real changes, as I said, there's one change you can make is you can actually change the underlying surface structure by, prescribing a different vegetation distribution and so on. Maybe you're planning to do something like that, or maybe not. But if you really want to make changes to the actual working of dry deposition, that requires code changes. And I don't think that you're going to do code changes. Are you? Oh, cool. Sorry, I didn't know. Very good. So you will play around with it. So in this part of my talk, I will briefly talk a little bit about about applications in research, how we are using our capability in terms of dry deposition. And the first example I've chosen was in a way ill-chosen, because it's the same one that Fiona has already presented before. But it's a really very important example, and so I'm just going to repeat that very briefly. The idea here is actually that the dry deposition of ozone, as I said, reduces the photosynthetic capacity of the ecosystems, which means they can't assimilate as much CO2 as they would be able to without the damage, and that leaves a larger portion of CO2 in the atmosphere, which contributes to radiative forcing. And in their study, Sitch et al. Found that by 2100, and using the most pessimistic scenario, the extra contribution of this this is an indirect forcing process, because it's actually you're not directly releasing CO2, but you're indirectly affecting the concentration of CO2 in the atmosphere. And we call these processes indirect forcings. Can be between half a watt per square meter to 1 watt per square meter. And to put that in a perspective, the direct radiative forcing, I think that's a bit high. That should be 0.45. I think that's a bit high. But that may be in their study. So the IPCC consensus, the most likely value, if you want to, of the ozone, the direct... Oh, sorry, I'm making a mistake here. This is the future forcing. I was thinking of the present day forcing. So the 0.45 watts per square meter is the present day ozone radiative forcing, and the 0.89 watts per square meter is the future 2100 ozone radiative forcing. My mistake, I'm sorry about the confusion. So basically what they showed is that the indirect forcing through ozone damages in the ecosystems can be as high as the direct effect, which is substantial, in a word. The second example I wanted to talk about quickly is a study we did for a project called SAMBA, which was the South American Biomass Burning Assessment, I think, something like that, acronyms, which was to look at the impact that biomass burning or forest fires can have on the Amazon forest in terms of functioning and health and so on and so forth. So we were looking at the impact of forest fires on atmospheric composition, on ozone production specifically, and then how much will that extra ozone that is produced through the wildfires, through the forest fires, how much can that actually damage the functioning of the Amazon ecosystem? So we were focusing on that region here, and this is a plot of the ozone concentrations from one of our Earth system models. This is the older one. This is HM2. So this is what HM2 would see in terms of ozone over the Amazon under normal circumstances, under a normal forest fire scenario. And you see that actually most of the Amazon area is exposed to rather low ozone concentrations, the range between 10 and 20. And I should say that our model has a tendency to slightly overestimate ozone. It's very, very difficult to get ozone right over these ecosystems, because measurements would indicate it's between 5 or nothing, actually. And models just are not capable of representing that environment that accurately. But this was intended as a sensitivity study more than a real-world case. We were just interested in how much the extra ozone from wildfires can damage the environment. And so we did a number of sensitivity studies. We varied the forest fire emissions from the actual case to nothing and to twice as much as there would be under normal circumstances. And you can see that actually when you increase the emissions of when you increase the fire emissions during, I should say, this is during the biomass burning season, August, September, October, there's a dramatic increase in ozone, and when you reduce them, there's a dramatic decrease in ozone. And here I'm showing the change in net primary productivity, which is a measure of photosynthetic activity, basically. And they are inversely related. So the more ozone you have, the less productive the environment is, and the less ozone you have, the more productive the environment is. So there's a clear connection in the model between more or less fire emissions and a better and worse functioning of the ecosystems. And what we, in terms of magnitude, what we could find that a normal fire season contributes to an extra of 230 teragrams of carbon emitted in terms of CO2, which is as much CO2 as the fires themselves emit. So the indirect effect of ozone doubles the effect. I'll say that again because this is a bit difficult to get your head around. When forests burn, an end product of the burning is CO2. So you're converting carbon that's captured in the biosphere into CO2 that goes into the atmosphere, and that will contribute to radiative forcing. At the same time, these fires emit species like NOx and ozone precursors, and so more ozone is produced than would be the case without the fires. And that ozone reduces the capacity of the surrounding non-damaged vegetation to take up CO2 because they are impaired in their photosynthetic capacity. They're not assimilating as much CO2. So as a result, as much CO2 is not assimilated as is emitted through the fires directly. And that's the indirect effect of ozone on these ecosystems. It's quite interesting, actually. We were, if you have any questions, please feel free to ask me at any time when we're going to the question section and also during the coffee break. It's time for me to actually think about finishing up. So I would just want to go through a few slides with you that sum up most recent work. I want to mention two things. There has been done work on the coupling to the ecosystem. Federico Centoni and David Stevenson in Edinburgh have looked very closely at many of these resistance terms. They have been working on adding missing resistances and disentangling the stomatal resistance from the soil resistance, which in the current model is actually coupled together, which shouldn't be the case. And in a different study, Maria and co-workers have done more work on coupling deposition to phenology, which is basically the seasonal change in the growing and the reducing in the vegetation. So they added a level of interaction between the land surface and the atmosphere in their work. And in terms of the ocean, deposition of ozone to the ocean, I already mentioned Catherine's work, which pointed towards the oceanic ozone deposition as the dominant term and a term that warrants more work. But at the same, a few years later, Ashok and co-workers from CSIRO in Australia have showed that we might actually overestimate the deposition over the oceans by quite a substantial amount. And they actually they made measurements. So they measured the ozone deposition to the oceans directly, and they found that, you know, our parameterizations may be substantially overestimating that term. So that puts this finding of Catherine's in a bit of a perspective. In future developments, this is about technical developments, model development, model code development, I should say. We are also planning to work on a tighter coupling with the ecosystems. We are trying to move to a more process-based deposition scheme, but ultimately what we are trying to move to is to a unified framework where we do emissions and deposition in one place and move towards something which is close to surface exchange. This is the long-term ultimate goal, and there have been first steps towards that goal already taken. And in terms of research, I think one emphasis needs to be on evaluation, making sure that what we do in the models actually makes sense. So there needs to be a lot of work and effort put into this. Hopefully we will also be able to do more measurements along those lines. And then, of course, we are interested in sensitivity of deposition to climate and to land cover change, but also of the climate and the land surface to deposition. As I mentioned before, you know, ozone damage, how does the land surface and the ecosystems evolve into the future under an increasing or potentially increasing air quality issue. And on my final slide, I'm just putting that up every time I talk about dry deposition. I want to draw your attention to the fact that there is a dry deposition working group in the UK that has as a remit to improve the dry deposition representation in UK models, and also to draw together the communities, the different communities, and make them talk together. Because people like working on oceanic dry deposition and dry deposition in the cryosphere are usually not working closely with us, who are mostly working over the standard land surface vegetated areas. And this is an effort to bring everyone together at the table and talk about things and developments. And if you're interested, we are very happy to welcome you in that dry deposition working group. There will be meetings, there will be presentations and so on. So watch that space if dry deposition is something that interests you in your work. And I'll leave you with the 3 ideas that I would like you to take home from this talk, and I'm happy to answer any questions if there are any. So thank you very much for your attention.